Today we're going to build a working BASIC interpreter in a single Java class. BASIC was one of the first programming languages, and our interpreter will support classic features, line numbers, print, input, let, ftgn, GOTO, for next loops, rem comments, and end. We'll parse the source file, build an internal representation, and execute it just like an old-school home computer. Along the way, we'll use modern Java features like regular expressions, lambdas, and the Neo File API. This is a complete, self-contained interpreter you can run from your IDE or terminal. We start by importing several standard Java packages. Beyond the usual java.util, we also include java.io.io exception and java.neo.file, files for reading the basic source file, java.util.regex, pattern and matcher for tokenizing lines, and java.util.function.byfunction to represent binary operators as lambda expressions. These imports show that we're using the full power of the Java standard library, not just collections, but also file I/O, regular expressions, and functional interfaces. The entire interpreter lives inside a public class called TinyBasic. The first inner structure we define is an enumeration called token type. It lists every possible token our language understands, numbers, strings, identifiers, and all the keywords like print, input, then, GOTO, for, to, next, end, and rem. It also includes operators, plus, minus, multiply, divide, power, comparison symbols, assignment, parentheses, comma, colon, semicolon, and end of file. Each token will be represented by a small token object that holds a type and an optional string value, for numbers, strings, or variable names. This is the vocabulary of our language. Next we implement the lexer class. Unlike many interpreters that process characters one by one, we use a single regular expression to tokenize an entire line at once. The pattern matches quoted strings, numbers, identifiers, multi-character operators like. Other identifiers become variable names. The lexer provides simple peek and next methods to consume tokens one at a time, plus and has more, check. This design makes parsing remarkably clean. Now we move to the abstract syntax tree, AST. We define an abstract statement class with an execute method that takes an eval state object. Every basic command becomes a concrete subclass. Print statement holds a list of expressions to output, input statement reads a number into a variable, let statement assigns an expression to a variable, GOTO statement sets a target line number for jumping, if statement evaluates a condition and conditionally jumps. For statement initiates a loop by setting a variable and pushing information onto a stack, next statement increments the loop variable and jumps back if the limit isn't reached, end statement halts execution, and rem statement does nothing, comments. Each class stores only the data it needs and overrides execute with the appropriate logic. Alongside statements, we need an expression hierarchy. The abstract expression class declares an evaluate method that returns a double. Concrete subclasses include number expression for numeric literals, variable expression for variable lookups, string expression for literal strings used only in print, binary expression for arithmetic and comparison operators, and unary expression for negation. The binary expression constructor takes a string operator and assigns the corresponding lambda function. This functional approach keeps the evaluation code compact and readable. To track the program's execution, we create a small eval state class. It holds a map of variable names to their current double values, a scanner for reading input, the current line number, a GOTO target, if any, a running flag, and a stack of for loop info objects. For loop info itself stores the loop variable name, the limit expression, and the line number to jump back to after the next statement. This stack allows nested loops to work correctly, with each next statement referring to the innermost for. The runtime state is the heart of the interpreter's dynamic behavior. The parseLine function takes a line number and the text after it, creates a lexer, and decides which statement to build based on the first token. If the line starts with print, it reads a list of expressions, strings or numeric, separated by punctuation. Input expects a variable name. Let, or an implicit assignment starting with an identifier, reads a variable and an expression. If processes a condition, then, and a target line number. GOTO reads a line number. For reads a variable, an assignment to a start value, a TO keyword, and an end value. Next reads a variable. END and rem are trivial. Any unrecognized pattern throws a syntax error. This parser converts each textual line into a structured statement object. The expression parser is a classic recursive descent implementation. We have methods for each precedence level. Parse_expr starts at the lowest precedence. Comparisons, calling parse comparison. Parse comparison handles equalities and inequalities, then calls parse addition for plus and minus. Parse addition calls parse multiplication for multiply and divide. Parse multiplication calls parse unary to handle unary plus, minus. Parse unary calls parse power for exponentiation, right associative. Parse power calls parse factor, which handles the base cases, numbers, variables, and parenthesized sub-expressions. Each method builds the appropriate expression node and returns it. This grammar gives us correct operator precedence and associativity. The main method ties everything together. It expects a file path as a command line argument. Using files.readString from Java and I/O, it reads the entire basic source into a string. The source is split into lines, and each line is processed. The leading line number is extracted, and the rest of the line is parsed by parseLine. The resulting statement objects are stored in a tree map keyed by line number, which keeps them in order. Then we create an eval state and begin execution. We maintain a program counter that indexes into a sorted list of line numbers. Inside the loop, we fetch the current statement and call execute. If the statement sets a GOTO target, we look up that line number and set the program counter accordingly. And next statements require special handling. For increments the counter as usual, but next may jump back to the line after the first statement. The loop continues until the running flag becomes false, via END or an implicit end of program. To compile the interpreter, we simply run javac tinybasic.java. To execute a basic program, we pass the filename as an argument, java tinybasic myprogram.bas. The interpreter reads the file, parses every line, and then starts running. For example, a simple basic program might print a message, ask for a number, loop from 1 to that number, and print each value. The interpreter handles input by prompting with a question mark, uses the for loop stack to manage iteration, and prints output with the print statement. Error handling catches undefined variables, missing line numbers, and syntax mistakes. This demonstrates a fully functional basic environment written entirely in standard Java. You've just witnessed the creation of a complete basic interpreter from scratch. We used regular expressions for tokenizing, recursive descent for parsing, an object-oriented AST, and a straightforward execution loop. This project touches on file I/O, Lambda expressions, generics, and control flow, all within a single Java class. You can extend it with additional basic commands, add functions, or even write a simple editor. The code is a great example of how a language interpreter works and how Java can handle the task elegantly.